just about the time when this rate law stuff starts to make sense, I'm going to show you another way of expressing rate laws. I can feel the excitement. What we've done so far is referred to as a differential rate law. You know, that kind of looks like this. R equals some constant times the concentration of your reactant raised to some order. It's usually a 1 or a 2, something kind of like that. And there might be more than one reactant, and we just string them all together. That's called a differential rate law. It shows how the rate depends on concentration. Another rate law, called the integrated rate law, looks at how concentrations depend on time. As time goes by, how are the concentrations changing? The rate law that we're going to focus on really is kind of dependent on the type of data that's collected in the lab. So let's look at some options. Okay, first order. Here's kind of what we had mentioned previously. The differential rate law looks at a change in concentration over time, and it's often expressed kind of like this, where you've got your constant, and then you've got your concentration of reactant, we're just calling it A, raised to the first power. So often it kind of looks like this. R equals K times A to the first. Here's the integrated rate law expression that focuses a little bit more on time. As time goes by, how do the concentrations change? In this guy right here, there is no mention of time anymore. And now we know that the rate is a measure of change in concentration per time, but I can't solve that equation for time, which is what we can do with the integrated rate law. What if I want to know the concentration of a particular reactant after 2 minutes have passed, or after 20 seconds have passed? How have the concentrations changed at a certain time in the reaction? That's what I can solve for using this integrated rate law. Now, here, the way that it's set up, I really like it, because this is slope-intercept form plus B. We're going to look at natural logs. Yippee! The natural log of the concentration of A at whatever time you want to study. Let's say it's after 5 minutes. 5 minutes after the reaction has started. I want to study the concentration of reactant A. So we'll take natural log of concentration at that time equals opposite KT. Opposite K, that's opposite of your rate constant, and then T is the time that you want to study, plus the natural log of concentration of A, 0, which just means initial. The initial concentration of A. I like this setup because it does match slope-intercept form, and often this kind of data will be graphed. This is kind of where we're going in the lab. We're going to come up with these graphs, and we're going to try to figure out changes in concentration over time and orders of reactants. It's going to be great. What I also like about this is that you can get the constant off a graph. The opposite of the slope should be the constant. That's kind of nice. Now be aware, that's not how it's shown in the AP packet. The AP packet kind of writes it like this. Natural log of A at time t minus natural log of A initial equals opposite KT. There's nothing wrong with that. It's fine to write it like that. Just be aware that one of the most valuable things you can get out of this expression is the value of the constant. If you're given graphical data, kind of like what they're showing down below, I should just be aware that the opposite of the slope will give me the constant. So even though it may not be written in slope-intercept form, you could rearrange it to show slope-intercept form, or just be aware But the opposite of the constant, or the opposite of the slope, is the constant. So here's what happens. We're going to get this data in the lab. We're going to let the computer just graph it for us. And then we're going to experimentally try to figure out how we can get a straight line between those data points. One option is to try just graphing the concentration over time. No, bummer, that didn't give me a straight line. Another option, 1 over concentration versus time. Nope, that's not a straight line. What about natural log? If we take our data, and we're going to change the axes, and if we find that the natural log versus time gives us a straight line, that's first order. So from graphical data, we're going to look for a straight line. When it's natural log versus time, that's first order. And we're just going to kind of play with it. We'll try each of these 3 options and we'll see which one gives us the best fit. And from that graph then, we can find the value of the constant. The constant is usually reported as a positive value. So again, if you have a straight line here and we find the slope, in this case it's a negative slope, we'll just take the opposite. And that should give us the value of the constant. Let's look at some data. Here's a good example. We've got the decomposition of N2O5. Excellent. Using the data given, verify that the rate law is first order with respect to our reactant, N2O5. Now, often, again, experimentally, we'll try to look for a best fit. We'll change the axes, and we're trying to figure out which option gives us a straight line. In this case, it's right here. Natural log versus time. And all we have to do to verify this is first order is say just that. The graph of natural log of our reactant, N2O5, versus time is a straight line. And they'll do this on the AP test. They'll give you the data and they might give you like different options on the graph. If you find that there's a straight line when it's graphed natural log concentration versus time, boom, straight line graph, natural log, that's first order. What else can we do here? Calculate the value of the rate constant, where rate equals the opposite of the change in concentration versus time. Report the rate constant with proper units. Now, technically, it would be better if this said natural log, because we're looking for the slope, but it's natural log of the concentration versus time. And it's kind of nice that in this data table, they already gave it to us as natural log of the concentration. Often, the data is just going to give you like molarity. And then we would have to plug it in as natural log. This time, we can just calculate the slope, huh? So to make it easy on ourselves, I don't know, let's maybe look at the first 50 seconds. All I want to do is calculate the slope. The opposite of the slope should be the value of k, the constant. So we've got slope equals. All right, we're going to go like final minus initial, I guess, technically. So this will be a negative 2.649 minus negative 2.303 all over 50 seconds. So this comes out to be a negative 0.00692. But the constant should be the opposite of the slope. They're usually reported as a positive. So my constant is positive 0.00692. And the units are just going to be 1 over seconds. Technically, by taking the natural log of the concentration, that number becomes unitless. So I really don't have any unit on the top, but I got seconds on the bottom. So 1 over seconds. Done. It was just the opposite of the slope. Now here's what you can do with this integrated rate law. I'm going to write the rate law the exact same way that it's used in the packet, because you don't have to memorize this. You're going to just want to look it up in the AP packet. In the packet, it's written like this. Natural log of A at time t minus natural log of A initial equals opposite kt. We can use this expression then to calculate the concentration of that reactant at a particular time in the reaction, after 150 seconds. All you got to do is sub in. Let's see what we got here. We're looking for this guy, natural log of the concentration at time t, or 150 seconds, minus the initial. And actually, if I go up here, I can get that from the data table. The initial natural log of A is like negative 2.303 equals opposite of K, the constant, 0.00692, 1 over seconds, times T, which is 150 seconds, the time at which we want to study the reaction. Now again, often the data table just gives you molarities, and then we would have to take the natural log of the initial concentration. But in this data table, it was already given to us as natural logs. All right, so we're going to do the math. We're going to simplify this as far as we can. Okay, so I'll simplify opposite kt, and then we'll take care of this negative 2.303 natural log of A at 150 seconds equals negative 3.341. And again, I just plugged all that in my calculator. I just did the algebra. That's decimal. I simplified both sides and solved for my variable natural log of A at 150 seconds. Now, if I want to get the concentration of A at 150 seconds, all I got to do is set it up. A at 150 seconds equals, remember this guy? E to the negative 3.341. When was the last time you whipped that out, huh? Now this should come out to be a reasonable number. 0.0354. Now we can kind of see if this makes sense. The natural log at 150 seconds was negative 3.34-ish. Well, that's what's listed on this graph. So if I were to go about 150 seconds, that's probably about right. Approximately negative 3.34-ish. What was it, 1 or something like that? But again, often they're going to ask you for the molarity, not the natural log. So then we can just solve it for the concentration of A. Just go e to the whatever you solved for. In this case, e to the negative 3.341. And now this is a more legitimate molarity. That's how you'd use this equation. It's used to solve for concentrations at particular times in a reactant.